Welcome back to our series on electricity and magnetism. In this episode, we're going to look at Ampere's law, a very powerful equation, one of Maxwell's equations that forms the basis of electricity and magnetism. Often it's referred to as the Gauss's law for magnetism. And if you recall, Gauss's law was a fantastic shortcut for finding the magnitude of the electric field anytime you could exploit symmetry. And Ampere's law will be no different. You'll have to be able to exploit certain symmetries of the magnetic field, but if you can, this will represent a powerful way to find the field. Okay, up to this point, we've only been able to locate the magnetic field from a current-carrying wire by using the law of Biot-Savart. And in essence, what we did in that case is we took a long straight wire that was carrying a current. We identified a location where we wanted to find what the magnetic field was. We drew a line representing the radius from the location where I wanted the field perpendicular to the wire. And basically what I wanted to do was find out how the field at this point related. And you'll recall, we identified a little piece of current. We called the direction ds. We integrated that together with the radial vector r hat, which indicated the direction. The cross product of those yielded an integral, which ultimately produced the size of the magnetic field. And you'll recall that we can use the right-hand rule to determine the result of that cross product. If I point my thumb in the direction of the current, then my fingers will curl around the current, representing the direction of the magnetic field. So in this case, there is a magnetic field at this point, B. It runs directly into the board at this point, and its magnitude, that is the size of B at this point, is going to be equal to mu naught times I, the size of the current, divided by 2 pi A, where A represents the radius. And this basically represents the magnetic field for a wire that's so long that we don't really have to worry much about the edge effect. As the wire gets shorter and shorter and shorter, you remember there were square root functions on this side of the formula that allowed us to find the magnetic field from any length of wire. But if the wire was long enough, then we knew that as we went further and further out, its contribution to the field would get smaller and smaller and smaller. And so this represents the magnetic field for a current-carrying wire at any radius perpendicular to the wire itself. You'll notice this is not a constant field. This is not like our magnetic capacitor that we've been looking at for so many of our visual experiments, where we've been looking at the force on a current-carrying wire and the force on a charged particle. Those were constant magnetic fields, and this will be anything but constant. As the radius decreases, the field strength will increase because it's inversely proportional. And that means the field lines become denser and denser as we get closer to the wire. If we drew in the actual field, we'd have concentric circles that were very close to each other, close to the wire. And then as we moved out from the wire, they would get further and further apart, indicating a diminishment of the field. Those lines, however, would move all the way up and down the wire. So there would be concentric circles that were everywhere, all along the length of the wire. Well, let's utilize this as a model to actually derive the new way that we're going to go about finding magnetic field. And it's called Ampere's law. Let's take a look at it. I'm just going to change the orientation of this so that we can work a little bit easier. So this will be the current traveling straight up. Basically, the right-hand rule tells me that the magnetic field is going to go through the board towards you on the right side. So over here, we would see magnetic field like this from this current-carrying wire. And of course, over here, it would come out of the board at me. So it would head into the board on this side and out of the board on this side. So that's how you would see it. You would see it coming at you from here and away from you on this side. So looking like this. Okay, well, let's imagine then one of those field lines. So I'm actually going to draw in the entire field line as a circle. Remember, this field is polarized. With my thumb pointing up, it definitely has a direction. If this represents the front of it and this here represents the back of it, then that field is going to the right towards me. It's going to the left towards you and circling around over and over again. Just like all magnetic field lines, it has no beginning and no end because it's not moving towards or away from monoparticles, it's circling the current that generated it. And that's where we're going to exploit to derive what we call Ampere's law. What I want to do is draw in a circle right on top of this field line. And that circle is going to represent what's called our Amperian loop. Now that loop will have a direction. So just like the field lines, this will be directed along the field. And what I want to do is I want to integrate that field along that distance. I, in essence, want to take a closed loop integral of B dotted with ds. And ds actually represents this path that I'm going around. Well, as we know, going out a radius A will give me a circle whose circumference is 2 pi r. What I need is the magnitude of the magnetic field at the end of that radius. And fortunately, because we have the law of Biot and Savart, we already were able to obtain that value. This is the magnitude of the magnetic field at this location. So ordinarily, I would be using this to find the magnetic field, just like I do with Gauss's law. But in this case, I can actually perform this integral. I can perform it because I already know the magnitude of the field at that location. So let's do this integral. Let's integrate around the full circle. And what I want to integrate is this. The B field. And the B field at that location is mu naught I over 2 pi a. And I want to integrate that around ds. ds then is little bits of this circumference. And of course, if I integrate all of them around a closed loop, what am I going to get? I'm going to get the entire circumference, 2 pi a. Not only that, but this dot product refers to how parallel the magnetic field line is with this vector ds. And because I've deliberately chosen ds to run along the field line and in its direction, this dot product returns the product of B and ds. That is, I don't have to do what I ordinarily do with dot products, which is figure out the degree to which the vectors point in the same direction and use the cosine of theta to control how large the dot product is. In this case, theta is 0 because these two vectors are absolutely parallel. Well, look at what happens when I finish this integral. It's the integral of the B field and the integral of ds, which produce 2 pi a. That whole thing equals mu naught times I. And there's the answer for Ampere's law. If I am able to construct an Amperian loop ds along the direction of any anticipated magnetic field, that integral will always equal the quantity mu naught I. That is, the closed loop integral of B dot ds is always mu naught, the permeability of free space, times I. If the B field is the same at every location, then I don't need to integrate for it, and I can pull it out of the integral. And all I have to do is integrate ds. That will always be a closed loop, which has a circumference. And that means I'll be able to calculate the size of the B field by simply dividing mu naught I by the loop that I have chosen. This is a powerful analytical technique because at this point we could actually use it to solve this problem. Now, as long as this works, I can say, hey, what would be the magnetic field around a current carrying wire? Well, I know the magnetic field will run in circular lines around it, so let's put an Amperian loop in a circle around it, parallel to the field lines. It will be an integral of ds, which if I integrate all the way around the circle will produce the full circumference. So B is the same at every point. It comes out of the closed loop integral of ds. And that will always equal mu naught I. Well, what is the closed loop integral of the circumference of a circle? It's 2 pi times the radius. So B times 2 pi times the radius will equal mu naught I, or B equals mu naught I over 2 pi a. So the question remains, Would you rather do this calculation or rely upon Biot-Savart and taking the integral of a cross product in 3D space? Now, just like Gauss's law for electric fields, there were firm limitations on when you could use it because you had to exploit the symmetry. You had to capture all of the flux in order to say that the electric field inside the surface was proportional to the enclosed charge. And you had to ensure that the electric field was always perpendicular to the surface and evenly distributed around it. If those things weren't true, then you didn't get access to Gauss's law. Well, the same holds true for Ampere's law. You can only exploit it when your Amperian loop features a constant magnetic field at every point, or at least a magnetic field whose value you know. And let's take a look just at a quick example of a simple magnetic field that we can't use Ampere's law for. And that is the magnetic field of a current carrying loop. Suppose I have a loop of wire and it runs around this location in space. Well, I know that the current carrying wire will generate little magnetic field lines that run around in circles on it. The problem is those field lines are going to radiate circularly, which means they'll all be closer together inside of the loop. And they'll all be further apart outside the loop. So this forms a non-constant magnetic field. The magnetic field lines still form loops, but this part of the field is weaker than this one. And so if I tried to throw an Amperian loop on top of it, I would find that I couldn't perform the trick of pulling the B out of the integral because it wasn't the same at every point on the circle. So you can see there's plenty of situations where Ampere's law will not come to the rescue and we'll still need the law of Biot-Savart in order to evaluate magnetic field strength.